Yeah, thanks for a nice introduction. I want to use a video. The
Oh,
reason is the internet is not so stable. So,
yeah,
just in case, thank you for
sure.
your understanding.
Thank you.
Thanks, Professor Jingxin, for your nice introduction. And thanks for the organizers to give me this opportunity to introduce our research work in the zeolite and catalysis. Good morning, everyone. And I would like to introduce our recent work focused on the porous structure and acidity improvement for the zeolite and in the catalytic research. The outline of this work of this talk mainly focuses on two parts. The first part, we want to improve the size and also diffusion, the structure of the big molecule normally involved in the biorefining, and for so of the zeolite, which can help us to improve their efficiency in the biorefining process. As we know, the majority of the microporous zeolites, they face the challenge for the big compounds, normally coming from the biomass-derived compounds. So therefore, if we are able to improve their structure and the porous for the catalytic reaction, so we are able to improve the efficiency in the biorefining. The second one is we developed the mesoporous silica, which are able to provide the confined structure, especially for the hard reaction, like dry reforming this type of reaction, to realize the superstability for this type of reaction for the middle catalyst. So we are going to the first. So the mesoporous zeolite, ZSM5, prepared to use the hard template carbon nanoparticles. So there are many different methodologies to produce the carbon nanoparticles. We are also able to change the size based on the ball milling and tune the particle size. So therefore, we are able to generate the different mesoporous ZSM5, use the different size, this kind of carbon particles. So we use a polymer and then do the carbonization to produce the carbon particles. And then we do the ball milling, then we are able to generate small carbon particles. And then use the two types of different sized the carbon nanoparticles used for the synthesis of mesoporous the ZSM5. Let's have a look about the particle size. The big particle size is around 40 nanometer, 39 nanometer, and the small one around 40 nanometer. So after we use this as a hard template for the synthesis, so we are able to generate the mesoporous. So after the measurement, the physical adsorption, we are able to determine the average pore size of this mesoporous ZSM5. For the big one, is around 35 nanometer, and for small one, around 13 nanometer. Both are quite close to the size of their template. So from the BET, it shows the typical this kind of mesoporous adsorption desorption, this kind of property, and also the crystal looks good. So from the TN, we are able to see for the small particle, carbon as a template, we generated small pores, and if we use a big one, so we can see a big like horse mesoporous like pores inside the zeolite particle. So from the NMR investigation, we are able to see how their local structure change if we introduce the this type of the hard template, different size of hard template. So we can see this is use a classic micro resistant 5. We can find they have only small amount of 6 coordinated alumina, and the majority of the aluminum species in the 4 coordinated in the framework, which contribute to the bronze acid side required by resistant 5 for reaction. So we used whatever the small particle carbon template or the big particle carbon template. There are no big difference of their local structure. The aluminum dominant in the 4 coordinated in the framework. The only very small amount in the 6 coordinated as the extra from alumina species. So from the acidity, this is a micro one. So that means there are no mixed porous introduced by the carbon like a particle. The dominant is the bronzine OH group at 4.1 ppm. So after adsorbed the like acetone nitride as a proper molecule, we can see they show a strong acidic size. But if we introduce like carbon template, then we generate a mesoporous, then we generate more this kind of external silano group. So this is reasonable. For the small particle, then the density of the mesopore should be higher, and then we can see they will generate more like silano group. The acidic size drop down, and but we still have a certain number of acidic size. The acidity is similar, so no change compared to the macroporous one, but the dominant, the silano group generated. If we use a big carbon and they have less mesoporous, the less ratio of the mesoporous compared to the small carbon particles. So therefore, we have still many bronzine OH groups, and which contribute to a strong acidic size, but have also increased this silano group. Okay, so for catalytic performance, so even the we can say so even the acidity, they have a bronzine OH group, so the acidic strengths are similar. Even the microporous resistant 5 have more like bronze acidic sites, but their performance is not very good. So they start the deactivation quite quick for the ethanol dehydration. So this type of reaction. And if we increase the pore size to the small, use a small carbon template, and the particle, if the mesoporous introduced, we can see that both the performance has been strongly enhanced, especially their stability. We start to generate a big coke and start the deactivation after the 30 hours. And but the big pores like 35 nanometer, or this is 13 nanometer, there are no big difference for the porous change in the mesoporous range. We also can find it here. The big like mesoporous have slightly increased the selectivity and the conversion compared to the small, this kind of a mesoporous like resistant 5. Then we used the big molecular. This is used like vanillation of the aromatics. So the size is much bigger than the ethanol. So a paraxylene or the methylene. So they have one have a 2 methyl group, another one have a 3 methyl group. So the size will be different for the comparison for the reaction. So if we use this benzene reacted like coupling with xylene, we can find the micro still very poor compared to the methyl to zeolites, but there are no big difference because the paraxylene is much smaller than the tri-methyl, this kind of benzene group. But if we use these aromatics with the 3 methyl groups, so the size increased, and then we can find very clearly the big pores will provide a bit like conversions compared to the small methyl pores. So in this case, we are able to change the pore size, and therefore we are improve the conversion and catalytic performance of the zeolite. But one challenge for these like carbon particles, so because which has a lower solubility in the water, and then so some of particles will condense on the bottom, so the efficiency for the hard template in the synthesis is quite lower. So therefore we are thinking about, is it possible to develop another type of the carbon material which are able to improve their solubility in the water and improve the efficiency for the methyl synthesis. So then we use the carbon quantum dots, because this is nanoparticle. Also, we are able to control the particle size, and which have a better solubility compared to the other carbon material, and also can be functionalized by the different chemical treatment. So therefore, we use different methodology to prepare different quantum dots group. So we list the 3 group here. So one of the group, this is have a big carbon quantum dots with average particle size around 23 nanometer. And then we have a second group of carbon quantum dots. They have 2 the average particle size. We mix them together. One is a 6 nanometer carbon quantum dots, another one is 9 nanometer carbon quantum dots. They mix each other. So, and then we have another one is carbon quantum dot 3. They have 3 different size. We have 3 different size of carbon quantum dots. Then we mix them together. It's a 5 nanometer, 8 nanometer, and 18 nanometer. So we use then this so like different size and also different group of the size of the quantum dots used for the synthesis due to the better solubility. So they are able to dissolve in a solution for the preparation. So after the synthesis, so we can see the particle size distribution, the similar like before. It's quite close to the quantum dot size. So for example, here we use these 3, like green one, we use the 3 different size of quantum dots grouped together. We are able to generate the 3 mesoporous, 3 sized mesoporous with microporous, like this and 5. So this is micro, this is 1 micro, and 3 mesoporous. So with the average particle size at 4.8, close to 5, 7.4, close to 8, and 17.5 nanometer, close to the 18. So similar, we are able to generate the 2 mesoporous group on the carbon quantum dots 2. They have 2 different size of quantum dots, and then we are able to generate 5.5, 8.5, 2 size mesoporous inside the lesion 5. And the last one, we generate only 1 mesoporous size, but the big pore is around 21.8, close to 23. They all show the good crystallization and also the porous structure. The TN also confirmed their latest, like they are also crystal like lesion 5. So the acidity and also local structure has been investigated by use the multiple solid state NMR. So for example, we can find the local structure dominated by the 4 coordinated alumina species inside the framework. So the crystal looks good. The similar, they only have a very small amount of extra framework alumina species at 0 ppm. And we also do the acidity test by using the 31P NMR for the zeolite after absorption of a TMPO. This is a very widely used the proper molecule to show the acidity. So then we are able to get the total amount, the acidic sites, and also the number of the porous sites. So we can find the acidic sites if we have more. If we have two like mesoporous structure, the acidic size is slightly increased, and if this is more mesoporous inside, so due to the high porosity and the slightly reduced total amount of acidic size. And finally, if we have a very big pore, this is also in the middle of the acidity. Due to the acidity is quite close, and then we are doing the catalytic performance for the triisopropyl benzene cracking. Then we are able to use this kind of big like molecular to probe the catalytic reaction. Then we can find for the conversion TIPB. So it's quite clear if we have 4 different pores, 3 mesoporous plus 1 microporous, the performance is the best. And also the selectivity is also much better compared to the others. And if we have the one big pore, one big mesopore, and it should slightly better, then this file will have 2 like small mesopores, and the micropores always show lowest activity. The similar for the ethanol conversion. So the catalytic performance is quite clear here. So the mesoporous, if we have 3 mesoporous plus 1 microporous, so we can find the performance is much better than the one big porous mesoporous and plus 1 microporous, and all the 2 mesoporous. And all of them are much better in the microporous less 5. So in this case, we are able to get a conclusion using the carbon quantum dots. We are able to generate the different porous structure and even the multiple mesoporous with one different microporous material, and therefore we are able to train and change their performance. So during the catalytic reaction, especially for the like zeolite, the silica alumina materials. So during the reaction and regeneration, this is quite hard to avoid the extra framework alumina species. So therefore, the Lewis acid sites generated by the extra framework alumina species, they will be coexisting with the bronze acid sites during the reaction. So some reaction will be competitive between the Lewis and the bronze acid site. So we're thinking about, is it possible, like a biocatalyst, they are using the cooperative sites to work together to generate like a better catalytic performance in the process. So in this case, we're thinking about, is it possible to cooperate Lewis and bronze acid sites together for better reaction? So previously, we are doing use a tin MSA51, and then we are able to introduce the dominant bronze acid side or sometimes dominant Lewis side, and optimize the bronze to Lewis ratio to show how they are cooperative. And finally, we find the existing of the cooperative between the Lewis and the bronze acid side will provide a much better conversion and selectivity for the catalytic reaction. We use the DHA conversion as an example. So then we are, so like here we can find the cooperative one is much better compared to the others. So whatever this is bronze acid side only or Lewis side only, or they are like combined together with a different ratio. And finally, we are able to generate an optimized one. So in this case, we are thinking about the strong Lewis acid sides from the aluminum, and because it's cheaper and normally available in the zeolite synthesis and utilization. So like the 3 coordinated alumina sites, extra framework alumina species, this is shown as the most stronger Lewis side in the zeolite. So we use that for the investigations, and then we find the catalytic performance will be much better, improved. So like here, so for the bioethanol dehydration, we can find in the without the strong Lewis side, so they need the 12 hours induction period. But if we introduce the strong Lewis side, balance of the both, we can find it's short around 1 hour for the induction period. It strongly improve the efficiency for the bioethanol to the ethylene. This is an important reaction because we know the bioethanol, the global production is over 600 million tons per year, and then which are able to provide renewable bioethanol to as a feedstock for the bioethylene production. Okay, so later we introduced this like 3 coordinated alumina bases to the mesoporous ZN5. And we also find, like here, we use the acidity. We use a TMPO to test the surface acidity. So we can find they have a strong porous side, and also which are able to generate the superacids between the correlation of tri-coordinated alumina and the 4-coordinated alumina. So therefore, we are able to generate the stronger, this kind of catalytic performance in the butanol conversion, and with a much better selectivity, like here. So this we can find they have 3 this time different reaction mechanisms involved. So we have superacids, which just start immediately for dehydration to generate carbonyl ions and drive the reaction. And also we have to generate aromatics like hydrogen carbon pore to produce the alcohol dehydrogenation to generate the olefin. And then Lewis side itself also can activate the alcohol to produce the carbonyl ions for the reaction. So this is a bio-oil biorefining process, and then we are talking about how this strong, very strong stability can be realized by the mesoporous materials like confined particles for some important reaction like dry reforming. So dry reforming is one potential like hydrogen produced process to replace the steam reforming use of water in the hydrogen production, because the majority of the natural gas rich country like Australia or Middle East, they are not rich in water, fresh water. So therefore, if we are able to use CO2 to replace the water in the dry reforming, it will be both like environmental efficiency and also the like economic benefits. But dry reforming always served by the sintering and coking information. So therefore, how to realize this? This is how to improve stability is a challenge. So we can have a look about the commercial catalyst, alumina supported catalyst. So if under 700 degrees C, this is normally dry reforming temperature range. So you will find, you can see the sintering starts quite quick, and the particles will drop together. But if we are looking about the mesoporous material like silica supported this kind of middle particle, and then you will have a totally different phenomenon. So like here, so we use MCM41 as one example, and you can see the metal particles, they are moving inside, and the small particles can growing, become a big one, but their size will be confined with the pore size. So they were moving, but cannot come out from the pores. And also you can see the like liquid, they are moving, they change the shape and moving inside the pores. And then we do the computer modeling and to find, so for this kind of like platinum surface, we are able to generate amorphous the atoms on the surface, and at high temperature they are running on the surface. So therefore the particle can move through the pore. And because of amorphous and the running of the particles, they can change the shape and to pass through the windows of the pores. But this phenomenon is very interesting for us because they are combined together, moving inside the pore, but they never become bigger over the pore size. Therefore, which are able to still keep the dispersion inside, block sintering. And most important, they cannot big enough, even whatever is small or big, they cannot coming out of the pores due to this kind of surface force. And then, because they can move inside the pores, so therefore, which are able to wash the coke outside, wash the coke inside the pores. That means they are potentially block the coke generation. So therefore, we do a very simple experiment at first to do a reforming, ethanol conversion reforming, and use the platinum on the porous, and this is the platinum on the non-porous silica, and then platinum in the alumina commercial one, and then we can find the latter two, they will lost activity due to the sintering, and the inside the porous performed very well. And later, we cooperate with Professor Johnson, and we prepared the catalyst in all particles inside, all nickel particles inside of MO71, and half outside, half inside MO71, and totally outside the MO71 porous. And then we can find if we totally inside, the stability is very higher. This here is 200 hours, but I think they did already over 800 hours or 1,000 hours for the very good stability. But if you mixture like inside, outside, or totally outside, the activity drop down. So then later we find if mixed porous working for that, then due to the high surface area, why not combine the carbon capture and the reforming together? So therefore we just introduce the promoter to adsorb the CO2, and then we are able to enhance the adsorption plus the dry reforming, which can improve their catalytic performance. And during the industry test, the large scale test, we find the M71 is porous, easily can be blocked, too small, and also the particle size sometimes too small, and it will damage the structure. So therefore, later we developed a new type of confined, the catalyst, nuclear catalyst. The nuclear particle size is around 7 to 10 nanometer, much bigger, and very good performance, even use the industry natural gas feed. So currently we already run over 1,000 hours, and the patent already in the process. Conclusion, and based on this kind of molecular understanding and also the structure modification, we are able to generate the catalyst from the fundamental and to solve the practical application problems. Okay, due to the time limitation, I just want to pass to the last few slides. And the collaborators, thanks collaborators, and also the students and the postdocs who are involved in the presented work. And thanks for research fundings. And finally, thank you for your kind attention, and also invite you submit your best paper to the National Science Review. Thank you. Thanks a lot.
Ziwei, you mute. I think you're on mute.
So, is there any? I'll start with small question, Professor Huang.
Thank you.
Yeah, in your first part, you mentioned you used CSM5 and porous CSM5 for the TIPB conversion, and I noticed that the stability of the 4 different catalysts will rise a lot, as well as the product distribution. I wonder which properties did contribute to the various stability and the product distribution.
Yeah, great question. So for my understanding, we do investigations after the deactivation to see what kind of the there's the problems. And then we say they have a totally different coke, like formation inside. So for some, for like 3 mesoporous plus 1 microporous, I think maybe it's better diffusion with a very logical, this kind of porous system. And diffusion can be improved. So they have less coke compared to even they have 1 mesoporous, a big mesoporous plus 1 microporous. So because maybe they have the connection, this kind of corner maybe contains more coke due to diffusion problem. So we think the diffusion problem is a main issue, and the acidity quite similar. Yeah. Thank you.
Okay. So any other questions? If not, I'm going to ask mine. Okay. I noticed actually you used a TMPO as a probe molecule for the for detection of the B acids on the on the material. And normally, I read a lot of papers and researchers using the Priding IR as technique to detect the A acids or the B acids. So what the difference and which one is more advantages, or they have different advantages?
Okay, this is a great question. For the Priding IR, it's quite popular because the IR is more available compared to NMR. So and also sample preparation is quite easy for the parroting, because if you have an in situ FTIR cell, and easy to prepare the parroting, but they have a disadvantage and some disadvantage for parroting, which are easy to distinguish Lewis and bronze side. But for the acidic strains and for the number of acidic sites, it's quite a challenge, because for the vibration spectroscopy, if you they have more impact factors to influence the intensity, and also some peak will come together to hard to do the decomposition. And with the NMR, the advantage is NMR only focus one nuclear. For example, if we do the 31P, we only see the signal of the adsorbed the TMPO, and no other signal can interrupt about the assignment or others. And the difficulty is for preparation, and also the NMR is not so popular like IR. But the good thing is not only we are able to distinguish the acidic sites, but also we are able to use a reference sample to know the quantitative amount of the acidic site. Compared to the IR, it's a little bit easy. And another thing is depend on the shift, the different chemical shift, we are able to estimate the strength of acidic sites. So this is the reason so TMPO is involved. Yeah, we can use that. Thank you.
Thank you. And I have to say, Professor Huang, though it's still online, I'm excited to see you. So in the future, I hope I have the chance to meet you in person.
Thank you. And also, just one sentence before I finish, because we're also looking for talent PhD student. We have a mini scholarship program at this moment. So if students are interested to do PhD in Australia, welcome. Okay.
That's good to know.
Thank you.
Yeah. So due to time limitation, thank you very much, Professor Huang.
Thank you.
Thank you.